All right. Hello again. So here we're going to move on from recursion and we're going to start looking at some sorting algorithms here. Um, for when we actually do the presentation of the sorting algorithms, some of them I'll show you recursively and sort of like loop-based versions there. So, and then like the really sophisticated sorting algorithms require recursion. So that's why we sort of did that first here. But we're going to start off with ones that run in n squared time because they're like those are kind of like the easiest ones to understand. They're the ones that like you could do yourself like by hand. If you're like, oh, I have a pile of books I need to sort here, you could probably do one of these algorithms. They're not the fastest, right? But they are the ones that are kind of like easiest to get started with here. Most of these can be used on like arrays or vectors, and mostly on linked lists. So they're not doing anything that would be particularly bad if you did it on a linked list, with one exception. There is one that sort of doesn't like quite play nice with linked lists, but we'll mention that when we get there. But first, I guess we should define what sorting is, just so that we know like what we're trying to accomplish, right? So first, a stab at attempt of like, oh, sorting a sequence, right? We're given a sequence means we want to put it into ascending order. So that if you look at all the sort of like elements of the array, right, each element is less than or equal to the next one here. Of course, if you wanted descending order, right, then just flip the comparison there. Like I'm going to do everything in terms of ascending. Descending, you just like flip a less than for a greater than. Excuse me. So what we're basically saying is like if you look at any sort of pair of adjacent elements in the middle of the array, right, we should have x less than or equal to y. If you grab like two elements that are right next to each other, x and y, the first one should be less than or equal to the following one there. Does that seem reasonable? Like think to yourself for a second. Does that seem like a reasonable definition of like, okay, if I start with something that's unsorted and I sort of like apply this rule to it there, will the result be sorted? So for example, like let's say that we're given this sequence here, right? So 12, 7, 15, negative 9, 10, 2, 14, 6. Definitely not sorted according to our definition. So we'll apply our definition to it and we will sort it. And we end up with negative 9, 2, 3, 4, 5, 6. Did I sort this? And it should be pretty clear that the answer to that is no, right? Like this is not sort of sorted there like that. Something went wrong. We followed our definition, but we didn't end up with a sorted output here. So our sorted result is wrong in two ways, right? So first is that there's some elements of the original sequence, in fact quite a few of them, that are missing, right? 12, 7, 15, 10, and 14, those are just like gone, like where'd they go? And then some new elements have been added that were not in the original. 3, 4, and 5 were not in the original, but they show up in this one here. So intuitively, it's like, okay, it's not enough to just put things into ascending order. You also have to keep the stuff that you started with, not throwing anything away and not adding anything new. So that leads to the correct definition of sorting, which is if we want to sort a sequence, we're going to construct a permutation of the sequence such that all the adjacent pairs are less than or equal to each other. So permutation means that we're just rearranging the existing elements. We're not allowed to add new things, and we're not allowed to remove things that were already there. We have to deal strictly with what we're given. We're not allowed to just like invent new stuff or throw away things that aren't inconvenient for us there. Now, when we sort of look at sorting algorithms here, we're going to classify them in a few different ways here. Of course, one big way is just like what's its big O worst case. So that can be n squared or n log n, or sometimes we can even do better than that. Right now, we're going to start by looking at the n squared ones, but we'll see the n log n ones sort of later on there like that. But beyond that, we also have the notion of an adaptive sorting algorithm. So an adaptive sorting algorithm is one that runs faster if you give it an input that is already kinda sorted. Like it should make sense that if like I give you something that is mostly sorted, you have to do less work than if it was just like random stuff there like that. So that means its best case runtime is going to be better than its worst case runtime for sort of partially sorted inputs. Right, partially sorted. Another thing we can have is it an in-place sorting algorithm? So an in-place sorting algorithm is one that uses O of 1 extra memory, which means it operates on the sequence itself. It doesn't like copy it into a separate place or need like some giant temporary array or something like that. It just sort of manipulates the sequence that it's given. And then finally we have the sort of notion of stability, which is a little bit more difficult to explain. So I'll need a few slides to cover that. So an intuitive definition of stable sorting is a sort is stable if you can use it in like a multi-stage sort. Like, okay, sort by first name, then by last name here. So to see why we need some kind of like, special purpose sort for this here, let's try this out and see what happens. So let's say I have this table of names, so first and last names, and I want to sort, again, by first name, then by last name. So my names are Bob Smith, Alan Jones, Jane Smith, and Zoe Jones. So I'm going to sort by first name, then by last name. So after sorting by first then last, what you would expect to see is, if I sort first by first name, then by last name, there's 2 Joneses and there's 2 Smiths. So all the Joneses should come first, right? Because J is less than S. And then all the Smiths should come second. The Smiths should come together at the end there like that. But if I did a sort by first name, then by last name, within the Jones group, Alan comes before Zoe because A comes before Z. So I should see Alan Jones and then Zoe Jones. 2 Joneses together, but A before Z. And then within the Smith group, I expect to see Bob before Jane. B comes before J. So let's try it and see what happens, right? So here's my unsorted list of names. So first I'm going to sort by first name. So I'm ignoring the last names. I'm just strictly sorting this by first name. So if I sort by first name, I have Alan, Bob, Jane, and Zoe. Alan Jones, Bob Smith, Jane Smith, Zoe Jones. Then I'm going to sort by last name. So for sorting by last name, I'm just going to look at the last names. I'm going to ignore the first names. Those don't exist for the purpose of sorting by last name, right? And I end up with Zoe Jones, Alan Jones, Jane Smith, and Bob Smith here. So I sorted these by last name, right? Like there's nothing wrong about how I sorted them. J comes before S, the Joneses are together, and the Smiths are together. But I didn't get what I expected. Zoe came before Alan, and Jane came before Bob. So what went wrong? Well, the problem is that when I did the sort for last names, right, I moved Zoe further than I needed to, right? I really only needed to move Alan down to being before Zoe, but I switched the order of them. I moved Zoe all the way up to the top there like that. So the problem is that our last step, our sort by last name, didn't use a stable sort. So a stable sort wouldn't have moved things so far. It wouldn't have put Alan after Zoe or Bob after Jane because we don't need to, right? So the definition of stable sorting is if 2 elements are equal with respect to the sorting order, so for example, the 2 Smiths and the 2 Joneses, then they'll appear in the output in the same order as they occurred in the input. So let's go back here and see what that is, what's that talking about, right? So the definition says if 2 elements are equal with respect to the sorting order here. So we're talking about the last name sort. So the Joneses are equal and the Smiths are equal. Within the Jones group here, the order of Alan comes before Zoe here will be preserved in the input here. So a stable sort would have put Alan first and Zoe second because that is the original order that they had there like that. Same thing goes for the Smiths. In the Smiths, we originally had Bob before Jane. So a stable sort would have kept Bob first and put Jane after it. It doesn't move things further than they need to move here like that. My original sort for last name was not stable, so it didn't do that. Alan Jones and Zoe Jones count as equal because we're comparing by last names only, so a stable sort would keep Alan before Zoe, like that, right? The stable sorts, again, like, you only care about them if you're doing a multi-stage sort, but sometimes they do require extra work, so that's why that's kind of important there. We're going to look at the n squared sorting algorithms first here, and you can kind of break them up into sort of two general strategies. So one strategy is we can look at all the things that we have, all the elements that we have there like that, and then for each thing we can figure out where it goes. So like you can think of this as like if you have a pile of books to sort and you want to put them on a shelf, right? So you pick up a book at random and you're like, okay, where's this book going to go? The author's name starts with A, so it goes on the left. The author's name starts with M, so it goes in the middle. The author's name starts with Z, so it goes on the far right there like that. So pick an element and then figure out where it goes. And then the alternate strategy is pick a position and figure out what goes there, right? Pick position I and figure out the element that goes there. So again, if you think of this in terms of like sorting books, you're like, all right, what book is going to go on the leftmost side of this shelf here? What is the sort of earliest author name that's going to go over here? So you look through your pile of books and you find somebody whose name starts with A there like that. So note that there's like always n elements and n positions. So this basically turns into like a pair of nested loops. So all of these kind of work out to sort of O of n squared times there like that. So I'll call these two strategies, where do you go, right? Like pick a thing and you're like, all right, where's this one go here, right? And what goes here? So imagine I have like an empty spot and I'm like, all right, what needs to sort of go in here like that? So for each of these things that we're going to talk about next, we'll identify which of these two strategies it sort of uses there like that. We're going to look at 4 n squared times sorting algorithms here. These will all be separate videos here, so like I'm not just going to like keep rambling for the next hour or something like that. So those will be selection sort, bubble sort, insertion sort, and gnome sort. These are not the only O of n squared sorting algorithms, but they're kind of like the sort of common introductory ones there like that. So if you want to, you can jump straight into the selection sort video at this point here, or you can watch them in any order really, but that'll do it for this sort of overview there.